Thank you. Um, I really appreciate it. Haizhao allows me to present my research here. So, and thanks for the organizer. And so today, I'm going to talk about some of my recent research. Um, I think the theme, so here's a summary. Okay, so let me get the summary like up front. The too long didn't read is, the summary is we are standing on the shoulder of giants. So we combine two state-of-the-art methods together, and we try to explain one of them. So and here is our problem. So the problem is parametric PDE. For example, what we have is we can think it's an operator equation. And this is our problem. We want to learn an operator T such that A is our coefficient. A can be in the Banach space or Hilbert space or whatever. And we want to learn a map, a data-driven method, so that we input an A. The method give a solution U. Okay. And also, another problem is when we have a measurement U, and we put U and maybe some measurement noises, the model should give us back A. Okay. So in my humble opinion, I think deep learning models are particularly suitable for these type of nonlinear mapping because it's pretty efficient in capturing nonlinear mapping. So okay, so let me first use this example. So this is a toy example, and it's from the Fourier neural operator paper. I think earlier Anima already talked about their seminal work in Fourier neural operator in this paper I clear this year. So this is our input, and this is our output. Okay. As we can see, this coefficient has a random interface and has these island-shaped interface. This is like satisfying some distribution. It's push forward of some pure Newman problem, so that at every point, the most likely around it is the same coefficient, but it has some probability to jump to another coefficient. So it formed this kind of a random interface, and this is a solution to this like a Darcy flow problem with a fixed forcing. Okay. Forward problem is using this as input and this as output, and inverse problem is using this as input and this as output. Okay. And when we have discretization, okay, so this is a famous sequence to sequence problem because we discretize, once we discretize the domain, and we have two sequences. So it's like, for example, we can have F1, F2 up to Fd, and each one of these are a vector of dimension n. So what we want to do is we want to construct a map from this dimension. So n can be very big. Okay, n can be like 100,000, but d is like fixed. So d is called the dimension of the latent representations, and n is the sequence length. And of course, it's related to our discretization. And if we can afford it, we can make it very big. Okay, so and here are some like operator learners. And these 4 papers are from the Caltech group, like mostly led by Andrew Stewart and Anima Anakuma. Okay, so Anima actually gave a talk earlier today. And the state, among which the state-of-the-art model is a Fourier neural operator. Is last one, this one. I mean, it generates lots of buzz in the iClear 2021. I think lots of people are talking about it. It's like it's surpassing models that 50 times the parameter of it. For example, ResNet, UNet, EfficientNet. and very powerful. And I think it's a milestone method. So in my opinion. And other operator learner include DeepNet. George talked about it earlier today. And other people are using like convolutional neural network to learn some operators. So here are some and many others, of course. But there are this is I think this is a booming new field. But so now let's talk about the real behemoth in the house. If we view the operator learning as a sequence-to-sequence problem, we have to talk about transformer. Transformer is arguably the most influential work in the last 10 years in natural language processing because it really achieves a sequence length invariant performance. So for example, if LSTM or other RNN, if we have longer sequences, the performance is naturally degraded because either in training or in evaluation, and because of the structural, this type of thing, because we have to know like previous input to know the next. But attention introduced in transformer paper is a state-of-the-art model. The computation is parallel, and it's extremely powerful. And we can have these, for example, in my in the title of this talk, we have these two Sesame Street characters. One is Bert, the other is Ernie. And I mean, these computer sciences people are really good at naming things. So Bert is a bidirectional encoder representation from transformer, and it's also a Sesame Street character. So, and the smallest Bert has 80 million parameters, so it's very big. And but let's play with it. So so this is a natural question to ask. So this is a figure I reproduced from the original transformer paper to better like represent its math. So let's ask this question. Can we apply the transformer to the operator learning problem related to parametric PDE? So this is a question we would like to ask. And it like transformer, this architecture has so many advantages, and it's very hard to resist to try it. So let's try it. Okay. For example, let's try it in this famous benchmark problem of Visit-Burgers equation. And we know the initial condition. So we know the initial condition, and we want to know what it's like at time 1. It's not like a time 0.1. It's marched so forward in the time. The dependence is totally like a non-linear. So it's not in the like and it's a nonlinear equation, of course. But it has a damping term, so it's kind of good. And this is what the problem looks like. So we have this is the solution, and this is the initial condition, and these are like randomly chosen for samples from the data set. And so let's try to apply it. So this is the result. So the first one is the classic transformer. So and we apply the original hyperbolic this positional encoding from transformer, and the next one is Fourier neural operator. And we can, so this is my own re-implementation. So it's a little better, but it's a little better than the original, but much better than the transformer. So this I tried this last year. The transformer had 22 million parameters. It's like, I don't know, 50 times than the Fourier neural operator, but it's almost like 100 times worse. Okay. So let's try to improve it. And we're standing on the shoulder of giants. Why I'm saying this? Because inspired by Fourier neural operator, if we view, so because I'm a coder, so I like to read other people's code, and from how Fourier neural operator applies this convolution, this Einstein sum on this matrix. And I learned that we can really linearize it very fast, because this matrix, so this matrix is an m by m matrix. I mean, so this matrix is an n by m, n is a sequence length. It's very long, it's very big. So its complexity computation is n squared by d when we multiply these two things together. I mean, so it's very costly. So it's, even though its performance is a sequence length invariant, but its computational complexity is very bad. Okay. So now follow, inspired by Fourier neural operator, we linearize it by a very simple way. And we can see that when we linearize in this way, it can be represented by this type of a Galerkin projection representation. So this is like our, trial basis, and this is our test basis. This is our incoming function. Okay. So, and also following this practice, we can simplify it a lot, and we can have this approximation property. And if we have learned finite element, and we can tell immediately this corresponds to a mixed finite element method, which is a saddle point problem. And the interpretation is extremely nice. So using natural language processing people's language, if we have a query, so some incoming query, and it's a function in some Hilbert space, and we want to deliver the best value. So the value is like the output, and it's our trial function space, and the key space is to test the response of this query, and it's our test function space. And the inf soup condition actually tells us the test function space has to be big enough so that we can unlock this best approximator. And exactly, we showed, like, use this inf soup condition to show the approximation capacity of this linearized attention mechanism. So, I mean, I don't know if ever people has done this before, but it's very nice mathematical theory. However, it doesn't quite work in practice, so we tweaked a few components. The first one is we changed the layer normalization scheme. So we work the layer normalization so that it's almost like something like this, for example. So I believe every one of us have seen this. This is nothing but, for example, Gram-Schmidt. The Gram-Schmidt divides by the norm square. So it's very like a layer normalization. We have to divide something. So we choose to apply layer normalization in this way, and then we apply this mesh-weighted normalization instead of a softmax. No softmax, very fast, okay? And we use Euclidean coordinates as positional encoding, just like a Fourier neural operator. And we, just like AlphaFold 2, so we concatenate it to multiple key structures of the network, and instead of just once, like the original. And what's the result? And here is example one revisited. So we compare Fourier neural operator. We re-implemented it a bit. We changed a few structures, and we use our Galerkin transformer. So we use 4 Galerkin attention encoder layer and 2 this spectral convolution layer from the Fourier neural operator. It's like we allocate 2/3 of the parameter to the Galerkin attention and 1/3 to the spectral convolution. What's the result? We increase the original performance by 200 times. I mean, it's crazily good. And I also compare with the random feature attention from DeepMind and Favor Plus from Google AI. And but because they are trying to approximate softmax, so I mean, so our point is removing softmax is the best approach for operator learning. So, and of course, the parameters are matching, just 500K or something. So, and the next example is we try to tackle the inverse coefficient identification for Darcy flow. I think this should be example 2. Sorry. So basically, we have our coefficient, and this is our solution. Given the solution, we try to infer the coefficient. So that's our problem. And again, so here is our result. So again, the Galerkin transformer achieved the best performance, but we can also see that the Fourier, curiously, actually, Fourier neural operator actually achieved the resolution invariant performance, even though it's worse than our model. But it's worth, noting, because the spectral convolution in frequency domain has some merit. But so recently, the community start to exploit a multi-level hierarchical attention, and which is our next goal. So that's it for my talk, and here are some acknowledgement.
Thank you very much